Welcome to this video lesson on the intersection of lines. You should be familiar with the equations of 3D lines before watching this video. If you have two lines in space, then they can be parallel and not touching. They could be parallel and intersecting or touching. If that's the case, they are coincident. That means they're on top of each other. They could be intersecting at one point, or they could just not be intersecting at all and not parallel. For two lines to be parallel, their direction vectors need to be scalar multiplication of each other, or the angle between them should be 0 or 180. For them to be intersecting, you should be able to find a parameter, in this case lambda and t, for which all the x, y, and z values or the coordinates of the line are exactly the same. For the lines to be skew, that means that they're not parallel or they're not touching, so that means both conditions above are not met. And for the lines to be coincident, that means both of the conditions above for them to be parallel and intersecting needs to be met. Let's start with an example. We're going to look at two lines and we are going to determine the relationship between them. The best way to start these questions is to figure out if they're parallel or not. And to do that, we need their direction vectors. In this case, I'm going to write both of the lines in a more familiar format, so in the parametric equation format. So our x is going to be 2 plus I times t, so that's 1 times t, so 2 plus t. Our y is going to be 2 plus t times 3, so that's 3t. And z is going to be 3 plus k, which is 1 times k, so 3 plus t. And we do the same thing for the other vector. And once we have that, we can determine the direction vector for both. For b1, we will have 1, 3, and 1 for our direction vector. And for b2, we are going to have the multiples of lambda, in this case 1 for x, 4 for y, and 2 for z. To test to see if two lines are parallel, we're going to use the same skills as we have in the past few lessons. So we're going to test to see if b1 is a scalar multiplication of b2. b1's components are 1, 3, 1, and b2's components multiplied by k are 1k, 4k, and 2k. And when we solve for k, we get that the k value is not consistent or inconsistent, meaning that the two lines are not parallel. Then we need to test to see if the lines intersect at any point. So what we're going to do is we're going to write the equations for them for x, y, and z. So x is equal to 2 plus t, and it's also equal to 2 plus lambda. Y is equal to 2 plus 3t, it also equals to 3 plus 4 lambda. And z is equal to 3 plus t, and it also equals to 4 plus 2 lambda. Once we have these, we can form three sets of equations for x, y, and z. We're going to take the right side of the equation and rearrange it. We will get t minus lambda is equal to 0 for x, 3t minus 4 lambda is equal to 1 for y, and for z we will get t minus 2 lambda is equal to 1. Then what we're going to do is we're going to use two of them to solve for t and lambda. In this case, I am choosing 1 and 2, but you could choose 1, 3, or 2, 3 to do this. So for using 1 and 2, I'm going to use elimination, so multiply 3 by equation 1 and subtract it by 2. It cancels out the t's, and I will get lambda is equal to negative 1. Then I will sub lambda is equal to negative 1 either into equation 1 or 2, and I will get that t is equal to negative 1 as well. It is not enough just to solve for t and lambda. We also need to check to see if the values are also correct for equation 3. In this case, t minus lambda, 2 lambda is equal to 1. So I'm going to sub in the values on the left hand side. T is negative 1. I'm going to subtract that by 2 times lambda, which is also negative 1. And so our left hand side will become negative 1 plus 2, which is equal to 1. And that's same as our right hand side, so it checks to be correct. Since the value of t is equal to negative 1 and lambda is equal to negative 1 is consistent for all the three equations, then we will know that the two lines will intersect for lambda is equal to negative 1 and t is equal to negative 1. Since we have the t value and the lambda value, we could use either the equation to the left or to the right to find our x, y, and z coordinates. Here in this example, we're using the t value and we are plugging it in. So for example, for x, it's x is equal to 2 plus t, or 2 plus negative 1, which will end up being 1. We can solve for x, y, and z and get our intersection point as coordinates of 1, negative 1, and 2. And we can set the lambda value to negative 1 as well and check to see if we get a consistent set of answers. And that's one way to check our solution. The summary of this lesson is fast forwarded here, so if you need to pause it and write any of the information down, please feel free to do so. And now we're going to look at another example. In this example, very similar to the last example, we are going to determine the relationship between the two lines that are given. The first step that I always use is to check to see if the two lines are parallel, and I am going to take the direction vector of both of these. In this case, B1 is 1, 1, negative 1, and B2's components are negative 2, negative 2, and 2. And we're going to test to see if one is a scalar multiply of the other. In this case, 1 is equal to negative 2k, 1 is equal to negative 2k, and negative 1 is equal to 2k. And we will consistently get that k is equal to negative 1 over 2 for all of these. And that means that the two lines for sure are parallel. Now, we have to also check to see if they intersect. If they do intersect, that means that they're coincident, they lie on top of each other. If they don't intersect, that means that they are just parallel and non-intersecting. To check for intersection, we're going to take the equations for x, y, and z from both of the lines. So x is equal to 1 plus t also equals to 3 minus 2 lambda. Y is equal to 2 plus t also equals to 4 minus 2 lambda. And for z, we have it equaling to negative t, which is also equal to negative 1 plus 2 lambda. We're going to take the right side of the equations and rearrange them. Here's an example for the x. So we get 1 plus t is equal to 3 minus 2 lambda. We're going to add plus 2 lambda to both sides. So we're going to have 1 plus t plus 2 lambda is equal to 3. Subtract 1 from both sides and we will get 2 plus t plus 2 lambda is equal to 2. We're going to do that for same things for y and z. So we're going to get t plus 2 lambda is equal to 2 and t plus 2 lambda is equal to 1. We're going to use equations 1 and 2 to solve for t and lambda and then use that to check the answer from equation 3. In this case, there is no solution because equations 1 and 2 are exactly the same, but equation 3 is actually not completely different, but different. So if we get a t and lambda value from equation 1 and 2 and plug it into equation 3, we can find many t and lambda values that actually don't work, meaning that there is no consistent solution to this. Since the values of t and lambda are inconsistent for all the three equations, that means we have no intersection and we do have parallel lines, but there is no intersection between them. I have left you with a practice question to try out on your own, and I will try to post a solution to this as soon as I can in a separate video. I hope that this video was helpful in giving you an idea about intersection of lines and when are they skew, when are they coincident, when are they parallel, and when are they intersecting. Thank you for watching.